Hi, everyone, and welcome to this session on the OpenVDB project. We've decided to split the session in two parts. So Nick and myself will give a brief introduction to the project, some of the latest activities. We'll make an announcement. And then the second half of this session will be sort of a live session where we try to answer questions. So you're really encouraged to use the Q&A chat window and give us as many questions as you can come up with. But we will talk about, we will give two presentations first. So we ask you to please have patience. And in the second half, we'll start answering those questions. So let me first introduce you to the steering committee for OpenVDB. So as you probably know, OpenVDB transitioned as one of the first projects to the ASWF a little over a year ago. At this point, we have 4 members. There is Nick from Double Negative, who's actually part of this presentation. There is Dan Bailey from ILM. There is Peter Kuka, who is officially still a member, but he's currently on leave. Jeff Lade, who is at Side Effects, and then there's myself, who's at NVIDIA. In case you want to join our weekly meetings, it's every Tuesday at 10 a.m. Public, so anyone can show up. And we also actually post. Sometimes we update the time, so you can follow the second URL on this slide to see as we might change or cancel a meeting. And finally, the minutes of the meetings are posted in the repository, the GitHub repository. So you can also go and sort of look back and see what we talked about and decided on. All right, so now I wanted to give you sort of a very quick introduction and actually a motivation for OpenVDB and sparse volumes in particular. So bear with me if this is too simple, but I think it does actually serve a good purpose. So as you probably know, it's relatively easy to design a data structure that's fast, a sparse data structure that's fast, right? We typically just need a very shallow tree, like a tile grid, that actually offers a guaranteed constant time access, which is sort of ideal. The problem with this approach is that the memory overhead of storing the list of blocks, the table itself, can get prohibitively large, and it actually doesn't scale this approach. So on the other sort of end of the spectrum, we have very compact data structures. And sort of the prototypical example of that is, of course, an octree that has ideal additivity. It's 2 in each coordinate direction. So it often produces fairly tall trees when you have a lot of resolution. And the problem with that approach is that navigating tall trees can be computationally expensive. So really the motivation behind the core data structure in OpenVDB is to try and strike a balance between these two extremes. And that leads to this data structure called a VDB structure, and it's sort of it's a hybrid. And this is a 1D illustration of a typical VDB data structure. And it's, as you can see, it's a 4-level tree, so it's very shallow. And the root node is the only node that's actually dynamic. The rest are dense with progressively smaller leaf nodes. If you want more details, you can look at the paper listed below. So the way that you typically extract values from a data structure, tree data structure, in fact, any tree data structure, is through a top-down traversal, right? So let's say we want to look up the value at XYZ. You typically navigate the tree starting at the very top, the root node, and you navigate through the branch until you have a hit, and you return a value. The good news is it's a shallow tree, so it should be fairly fast compared to, let's say, an octree. The bad news is the first node is a dynamic node. It's a root node. So that actually has a computational cost associated with it. So VDB actually makes use of a technique that I believe is pretty unique to this data structure. It allows you to do not top-down, but bottom-up traversal. And the idea is very simple. Suppose you've done one axis already. What you do is you cache the pointer structures of that traversal, and for a subsequent access, you do a few bit operations to check and see if the subsequent access falls in the same leaf node. And if it does, well, then there's no traversal involved. You immediately return the value. If there's a miss, you move up to the second entry in this small hash table. So it's a common ancestor of the leaf node. And you perform another check, and if there's a match, you go down and then you return the value. So the idea is that you, on average, completely avoid the overhead of the root node, and it actually, on average, produces a constant time access, which is great. So it's fast. So these are some of the highlights. So the VDB data structure is unbounded to within the bit precision of the coordinates, which is typically 32-bit signed integers. It's compact both in memory and on disk. It offers fast random access and sequential access. We also have our own file formats, and we have our own codecs to make sure that the footprint is very small on disk. And the fact that it's a native, that it's a tree data structure actually means that it also has a native acceleration structure, which can accelerate many different applications like ray tracing or even things like Boolean operations. It does have quite a lot of external dependencies, and that, among other things, means that it's actually limited to the CPU. So OpenVDB has enjoyed over a decade of adoption in the VFX industry, and these are some of the third-party software that have adopted. Most of them are actually renderers. So most people are probably more excited about the tools that come with OpenVDB and not so much about the data structure. And there are a lot, far more than we can cover in this brief presentation. But at this point, we're actually over 100 different tools that have been developed over the past 10 years. There's one tool I just want to call out because we actually released it last week. So we just released version 7.1. 7.1 is a big release. It has far more than what I'm going to tell you now. But this is one of the new sort of tools that we added in this release. And it's a new way of computing signed distances and also computing or extending attributes off surfaces. So it comes in many different flavors. There are these two tools that allow you to go from an arbitrary scalar field. It could be a fog volume, it could be an existing signed distance field, and then it produces a narrowband signed distance field very, very efficiently. There are two other flavors that actually allow you to take attributes that are defined on an isosurface and sort of extend them into the embedding of the surface itself, which can be very useful. So for instance, it could be you have velocities on the surface, but you actually need to have velocities associated with values that are outside of the surface. These two methods will do that. And there are combinations of these four methods that actually perform both tasks at the same time. So it both extends velocities and also attributes from the surface. And finally, there are two methods that actually sort of complements methods that we already have, but it turns out these are significantly faster. So we can take an existing signed distance field, narrowband, and we can dilate it, sort of inflate it, make the narrowband width wider. And as a completely new thing, we can also extend a signed distance field into a mask of another grid, which is a completely new feature. All right, so at this point, I'm going to make what I believe is a pretty exciting announcement for OpenVDB. So as I mentioned before, OpenVDB was from the onset sort of developed for the CPU. And today, NVIDIA is actually sharing a library called NanoVDB that was developed actually since the beginning of this year when I joined NVIDIA. And it's the first attempt to try and take some of the workflows in OpenVDB to the GPU. You should really read something into the name Nano, right? It's not an attempt to take the full OpenVDB library and port it to the GPU. This is taking sort of a small subset of problems. Specifically, it's looking at things like rendering, real-time rendering and ray tracing, and also things like collision detection. So what is it? It's essentially sort of a snapshot of an existing VDB data structure, reshuffling the memory into a contiguous block of memory. And then it also gets rid of pointers. So it's very efficient to copy between CPU and GPU. It offers the same constant time random access that we looked at earlier that you will find in OpenVDB. In fact, it turns out that they're slightly faster in NanoVDB than in OpenVDB, simply because it's a more nimble implementation. It has a few extra things that OpenVDB does not have, which is specifically to accelerate ray tracing. So it bakes in metadata in the nodes that accelerate things like volume rendering and ray intersections. So it has bounding boxes of the active values at every single node, and it also has statistics like min-max values. It supports all the types that you will find in OpenVDB, including points with arbitrary attributes. So point index grids and point data grids are also supported in NanoVDB. Another thing that's quite exciting is that it's virtually agnostic to the platform. So it's implemented in both C++ 11, and also there's a C99 version that Jeff Lade actually ported. The core data structure itself is a single header file. So in theory, your client code only needs to include a single header file, and this header file has no dependencies. Like optionally, of course, you can have a dependency on OpenVDB in case you want to go from OpenVDB to NanoVDB. But for a renderer to pick up NanoVDB, you actually don't have any other dependencies than this single header file. It's using explicit memory alignment, so 32-byte alignment, which is required so we can tap into all the different graphics APIs out there. So it supports CUDA, Optics, OpenGL, OpenCL, GLCell, and SPURF. It also has a CPU fallback, so it works equally well on the CPU and the GPU. And currently, NVIDIA are also working on adding support for DirectX. That's coming soon. There's also a fast mapping between the two, and we can actually do round trips, so you can go both from OpenVDB to NanoVDB, and you can go back again. All right, so it also comes with a separate file format. It's not that we are sort of promoting the file format of NanoVDB to replace OpenVDB, but it does allow, as I mentioned before, it does allow applications like a renderer to only depend on the NanoVDB library itself, in case you want that. So as I said, we can do serialization in both directions. We include a few functions in the library as well, particular to cater to rendering. So 0, first, second, and third order interpolation. There's also the ability to actually generate NanoVDB grids out of pretty much any other volumetric data structure without necessarily converting to an OpenVDB first. This is what's called the grid builder. There's a very advanced and cool renderer including that was developed by Will Brightway at NVIDIA. That's actually included as a demonstration of how to use NanoVDB with all these different graphics APIs. And as you probably noted, it's not that NanoVDB only supports NVIDIA's API, right? So it's also OpenGL, OpenCL, and some of the other ones. So it's in that sense, it is truly agnostic. And there's also acceleration for ray traversal and sort of skipping of empty space, this thing called an HDDA, hierarchical digital differential analyzer, which is actually an idea that came from OpenVDB. So it's been ported. It's actually a different implementation, and it turns out to be outperforming the one in OpenVDB. So these are some, these are some benchmark tests. It's just, these are actually very old, but they still hold up. So this is ray tracing the Armadillo. It's casting close to 2 million rays per frame. And the first thing you'll note is that conversion from OpenVDB to NanoVDB is really fast. It's about 30 milliseconds in this case. And you're seeing different computational times for single-threaded CPU, multi-core CPU, actually 44 cores, and then the acceleration that you get from using the HDDA. And to sort of make a long story short, for this particular example, we're able to ray trace over 1 billion rays per second, which is quite fast. This is another example just to show that it really doesn't depend much on the complexity of the model. It also has close to 2 million rays, and again, it's achieving more than 1 billion ray intersections per second. So this is full-on ray level set intersection. So we're obviously not rendering a mesh; we're actually rendering a level set volume. This is a screen session from Will's viewer that we are including. So you can point it to an OpenVDB file, you can point it to a NanoVDB file. A NanoVDB file, of course, can encapsulate many different grids of arbitrary type. You can, on the right-hand side, you can actually have a drop-down menu, so you can drop down and pick different graphics APIs. So there's CUDA, optics, there is Intel's thread building blocks, so the CPU, and so on. And you have the frame count, you have statistics, and you have drop-down menus where you can sort of switch between the grids. So this is the Disney Cloud, and of course we get interactive frame rates, which is sort of the main point here. It's obviously not a production render; it was never intended to be. But it's great for debugging. It's great for a sort of example and starting code in case you want to know how to use this, let's say for OpenCL. There are also lots of examples included. I'll point you to how to get to the software at the end of this presentation. So this is importing a point cloud. And yeah, I think I'll move on to the next slide. So this is actually an internal application of NanoVDB. So Andrew Rittmeyer has developed a really cool interactive fluid solver called Flow, and he was able to pick up NanoVDB and use it for sourcing in the span of a couple of days. And he's able to source fuel on the left-hand side and smoke density on the right-hand side at about 1 millisecond per frame. So random access is very fast on the device. These are two other examples. These are kind of silly examples, but we really wanted to sort of stress the point that the ray tracing performance is virtually independent of the complexity of the model itself, in the sense that the VDB data structure offers constant time access. So on the left-hand side, you're seeing a level set of volume representation of a hairball using 2 billion voxels, which is, granted it's overkill, but it sort of gets the point across. We still get interactive frame rates. And on the right-hand side, we have, again, the Disney Cloud, but at a much higher resolution than you saw earlier. All right, so I really want to thank, obviously, NVIDIA for contributing this to the OpenVDB project. But I also want to thank a number of other companies that helped us sort of mature it and gave feedback, in particular Side Effects, ILM, and Pixar. And then I want to call out a few people. So especially Will Brightway has been an amazing collaborator. As I mentioned, he wrote the included interactive ray tracer. And he did a lot of other things as well. He did the CMake and helped with the memory alignment and stuff. Jeff was a great contributor as well. Jeff, who's actually on the TSC committee, he ported the first C++ implementation to C, and actually integrated NanoVDB in the next major release of Houdini. So it's already on the way. There's also Andrew and Frank that were very helpful. They're both at NVIDIA. So in case you want to try it out, I should say that the release that we have today is sort of a beta release. It's not a production release. It still needs to undergo some changes. We need to add DirectX support. We also need to go through the regular sort of code review, but it's available. It's actually exists in what's called a feature branch in the OpenVDB repository. So just check out the repo and check out the feature itself. So it's called feature/NanoVDB. And we also have a live blog that's hosted at NVIDIA that discusses NanoVDB a little bit further and actually shows some performance tests and also some of the examples. So that is it for me. I think it's over to you now, Nick. I'll just stop sharing.
Sure, awesome, thanks, Ken. Yeah, just a reminder, any questions, please put them in the Q&A and we'll get to them afterwards. But yeah, we are watching it. Thank you very much, guys, for tuning in. Thanks, Ken. Cool, so I'm gonna give a very brief recap and presentation on OpenVDB AX. For those that are unaware, I'm going to do a bit of a history, very brief history of the project, where we're at today, and what the project is, and also what we're currently working on, where we see the project going. So super quick recap. OpenVDB AX was open sourced at DigiPro in 2018. It was always intended to be incorporated into OpenVDB, and it's something that the TSC wants to do. But since the TSC's creation, roughly around the same time, we've had a lot of stuff on the backlog to work through. So it's been a bit delayed, but I think we see a path in the near future to get OpenVDB AX into the core repository. It currently exists as a feature branch, and I'll share links for this at the end of the slides as well. AX itself, for those that are unaware, is a just-in-time compiled expression language for focused around manipulating geometry attributes. It aims to provide compiled time C++ equivalent performance, but also provide the portability and deterministic behavior associated with an expression language, so you can plug it into a variety of applications. And it's domain specific for VDB, which is half true. The language is agnostic, technically, to the underlying primitive types. But since its original design, it was always intended to be specific for OpenVDB points and volumes. And focusing on that allows us to tailor the language features to better act on those kind of data types. And I don't see that changing anytime soon. So this is a super simple example of how AX can be used, and also kind of highlights why we wanted it in the first place, why we came up with the idea, why we worked on it. So this is a very basic OpenVDB simulation. We've got OpenVDB points being depicted through a VDB velocity field, a level set representing the collision. And it's pretty boring, it's pretty smooth. So one technique that we could use to make this more interesting is by injecting some kernel noise, injecting any noise at all really onto some of the particle velocities within a certain scale. And this is kind of what that looks like in C++. You don't need to be able to see the code here. This is more just to highlight how much boilerplate there is and just stuff you have to do before you can actually get to the interesting parts of your operation, which is basically running your per point manipulation and altering those velocity values. And you can kind of think of AX as a window into that side of interfacing with VDB data, and it handles everything else for you. And here's what the code looks like in AX. So this is the equivalent code in AX. Just to kind of talk through a bit of the syntax. Hopefully this isn't too unfamiliar with other coding styles. Looping over every point in this case. This $, syntax is pulling from user-defined parameters. And then we have a little function here that's building some noise and applying that to point velocity attributes. This could also run over a VDB velocity field, but in this case, we're running over points and accumulating velocity attribute with this syntax. And this is what the result looks like. So yeah, fairly simple kind of example, but I just wanted to show everyone that's unfamiliar with what the language looks like and what the project is, how it can be used to influence VDB data. Cool. So I want to spend the majority of the presentation talking about new features and where the project's going. The first thing we've done is documentation, which might not be the most exciting thing, but it's definitely one of the most useful parts of the new release. It's currently hosted on my personal GitHub, but will be moved into the OpenVDB docs when the merge is complete. So please check that out. The language docs are looking pretty good now. Still a lot more work needs to be done here, but it's going to be a work in progress up until that gold release. Other new features. So previously, you could only iterate over voxels within a VDB. You can now specify any tree level within a VDB data structure to execute over. So if you remember back to Ken's presentation, you can choose any node level within a VDB data structure and iterate over those. And that allows you to manipulate every value in a VDB. And we've just made a bunch of improvements and fixes, which you can also check out at the changes log. And I'll provide that link to the end of the presentation as well. One of the other additions we made is the introduction of this header file. So for those that are familiar with the project before, to run like a full AX pipeline from parsing, compiling, code generation to execution, you had to interface with a few different parts of AX. This kind of wraps all that together. So at the C++ in C++ API, you can now run a single function and incorporate that into your programs. So I just want to demo that super quickly. So this is a really hammy example, really simple file about, simple example where you can read in an OpenVDB file. It's not doing anything with it, and then just writing it back out. And then to incorporate AX, we can step through this particular code on the left. We're going to include AX as a header. We're going to initialize AX in a similar way that you initialize OpenVDB. We can then run any custom AX code. So here, we're looking for a surface attribute or grid. Attribute if it's points, grid obviously if it's a VDB volume, and we're accumulating just a small value onto that, and passing in the grids that we've read from the file, making sure we uninitialize AX, and then writing everything back out to disk. So hopefully that demonstrates how simple it can be to incorporate AX into existing VDB workflows. So a couple of things that we're working on that aren't currently released, but we'd like to get out as soon as possible. As I mentioned, AX was a bit in feature lock to try and help with the adoption into the OpenVDB project. But since then, we've added we're working on a few new features. The first is attribute function syntax. And this syntax is subject to change, so this might change before its release. But the idea here is to be able to call functions which are specific to a primitive type and have specific behavior for that primitive type. So in this example, all these functions that you see here that are being called after this at surface syntax are specific for VDB volumes. So the first four here, we are retrieving arbitrary coordinates and performing arbitrary samples from a coordinate. The next three here are retrieving transform information from a volume. And the last two here are querying whether or not a particular coordinate is a voxel, which will return false if it's a tile or another node type, and also whether or not a node is active or not. And you can see with the last few functions here how focusing on VDB-specific functionality lets the language, leverages the language to be able to focus on more specific VDB features. So for example, the activation kind of node masking of a VDB, or whether or not a VDB is a node is at a particular level within a VDB. Cool, so this is a quick demo. I'm just gonna pause it. So this is a super quick demo in Houdini, which demonstrates these new features. So I'm reading in the Dragon asset that you can get from the VDB websites. And on the left here, I've got a smooth operation, forming a mean filter with within 5 voxels. So with these new operations, you can construct your own filters, you can match existing functionality, and you can extend it as well. So if we jump into this little subnet here, so for anyone unfamiliar, this node network on the right is going to try and match the same network on the left. This is a VDB AX SOP, which is part of the software that's publicly available. On the right here, you can maybe just make out the kind of code that's being run, which is this node that's not attached to anything. And this just simply demonstrates how a naive implementation of a mean filter, which is accumulating neighboring values and forming an average and then writing to the original level sets. On the left here, instead, we have these 3 AX nodes, which are chained together, which perform individual mean filters across this VDB and are gathering voxels in a particular axis, summing them together, averaging them, and writing them back to the level sets. And the idea here is that that node chain on the left matches the result exactly, which hopefully you can see now. So this isn't a particularly, perhaps not a too interesting example in terms of new functionality, but hopefully you can immediately see how just by accessing the different kernels, the different ways that you're looping over voxels, you could manipulate this mean filter and change perhaps the width of one axis, the scaling of one axis, or incorporate a whole different type of voxel lookup pattern. Lastly, just to cover where we're looking to take the project. So the first major thing is point volume interaction. Currently with AX, you have to only execute over VDB numerical volumes or VDB points. This is a bit annoying because with things like sampling, it's such a common operation for you to be able to sample from a points position onto another points attribute. So this is definitely, I think, our #1 priority, to be able to incorporate different volume functions with points and vice versa. A metadata executable. So executables in AX are linked to the geometry that they're accessing. So the two current executables we have are points and volumes. A metadata executable would allow you to iterate once over each individual VDB, still provide you read and write access to that VDB, but also allow you to write completely arbitrary metadata to the grid, which supports metadata, read from that metadata and perform wholesale operations across a VDB. User functions. So we spent a long time improving the C++ API for developers to be able to customize how you can inject C++ bindings into AX. So that's come a long way. And the reason we did that is because that's one of our first ports of call to be able to extend AX's functionality. Just very quickly, we have a complicated C++ method, but if it's purely mathematical, we can quickly inject that into AX and that becomes available. However, what you can't do is customize and define user front-end functions currently. So that's definitely on the roadmap. Python bindings. Python bindings do exist in the standalone repository, but they probably won't be part of the original merge into the OpenVDB repository. They need a bit of work, but they do allow you to run AX through Python. So you can use the Python library that VDB provides to read in VDB grid. You can use these bindings to then call AX from Python. And finally, NanoVDB support, as Ken has announced. We would love to be able to, instead of targeting points and volumes on the CPU, target NanoVDB backend kernels on the GPU. AX, as far as the language is concerned, wouldn't change. You'd still write the exact same code, but this would allow you to manipulate, write custom kernels for NanoVDB data types. And that's everything. Yeah, so if you have any questions, please let me know. And if anything doesn't get answered, feel free to email the dev alias here. I just want to give a quick shout out to Rich Jones as well. I think he's might be listening, but he was also a big part of this entire project and is continuously working on it as well. In terms of accessing the project, it's in a bit of a weird transition because we're still getting it into VDB. You can access it as a standalone project through the DNegs GitHub, or you can access it as a feature branch through the Academy Software Foundation's fork of OpenVDB, where it will be migrated to. The DNeg repository will be retired once that's completed. That's everything. So I guess now we can move on to questions. Before we do that, what I'm gonna do is pull up a more generic roadmap for OpenVDB. I should probably not call this a roadmap. This is more of just a bunch of things that we have discussed over the last few years. We know there is interest in, and we would love to pursue further. So, as well as questions, if anyone has any comments, any thoughts, if there are things here that you would like to see, or if you just want to give something a +1, please just please put it in the chat. But yeah, I'll hand over to questions now. Let's have a look.
Cool. So I think the first question is from an anonymous attendee. It asks about, I'm assuming this is related to NanoVDB. It asks about WebGL, if WebGL is supported. It isn't today, but it's actually one of the things that we're looking at. So there's a good chance that it will be. Oh yeah, actually, I forgot. There's one name that I forgot to add to my list of acknowledgements. So Yomning Hu, I might actually be butchering your name or your pronunciation. I'm sorry, but he provided the soft body simulation that you saw in the beginning of the NanoVDB presentation using TaiChi. So he has also added support for NanoVDB in TaiChi. Let's see.
I just want to make sure, Ken, can you just see the roadmap right now? Is that okay?
Yes.
Good. Okay. Cool.
Do you want to talk about that, or do you want to go through the list of questions?
I just wanted to make sure that that you were seeing just the roadmap, so I can bring up the questions as well. Yeah, feel free to keep going.
Right. Cool.
Oh, cool. Yeah. So I can see. So the next one is how AX compares against the TaiChi programming language. Is there any comparison against it in terms of performance?
That's a good question. There are two very different things. So TaiChi is a high-level programming language for simulation specifically, whereas NanoVDB today is specifically for VDB, and it's specifically targeting real-time rendering in a way that's agnostic. So it's a little bit like apples and bananas. You know, it's possible that they will overlap more in the future, but today I think it's very difficult because NanoVDB today cannot do the simulations that that TaiChi can do, and TaiChi can't do the real-time rendering that NanoVDB can do. So yeah, I don't really know how to answer that question. But if you're interested in benchmarks specifically, the blog post that I mentioned, the one that's hosted on NVIDIA's website, actually has some benchmarks, and the repository itself has several benchmark tests that you can try and run.
In terms of AX in comparison to TaiChi, it's not something we've actually investigated. TaiChi, as far as I understand it, attempts to solve a similar but slightly different problem. AX is more designed to manipulate attributes, run the specific kernels per attribute on a very on a more granular level, whereas TaiChi you're able to build entire solver frameworks out of. I imagine there is some crossover, and I know that TaiChi also is targeting similar, compile time parallel performance. So I'd like to think that they're very similar, because in our benchmarking against C++ code, we come out very, very, very similar. So if TaiChi is doing the same thing, then I'm not sure there'll be too much difference.
Right. I see that's a question about support for Metal. And it's the same answer as it's not in there today, but we're working on it. It definitely should be supported. So the goal is really to try and support as many of these APIs as possible without, there's some APIs that have some restrictions that are tough to work around. I believe Metal has a limitation in terms of 64-bit ints and floats, but we can probably find a workaround that and only support single precision grids. I don't know, but it is something we're working on for sure. Nick, feel free to pitch in.
Oh yeah, sure. Sorry. So one by is the NanoVDB viewer available to download? Is it open source? Yes to both. Yes.
Yes, it is.
You have to check out. It currently exists as a feature branch in the Academy Software Foundation's OpenVDB repository.
Right. Actually, I think what we'll do is we will make a little post on the OpenVDB website, sort of announcing that NanoVDB is available, but also tell you how to access it, how to get it. It's quite simple, but we'll spell it out. What else?
Lots of questions on NanoVDB. These are mainly for you, Ken.
Right. So I think a common thread in these questions are sort of related to simulation. Like, will NanoVDB be able to do simulations in the future? That's a good question. So I should emphasize that the data structure itself, the linearization, when you go from an OpenVDB to a NanoVDB, is actually, it's sort of a snapshot. So it's not a dynamic data structure today on the GPU. So we will have to add changes to support dynamic trees. That's not to say that it's impossible. And I should also, for full disclosure, say that NVIDIA is actually working on something of this nature. But I can't really say much more than that. So it is coming in one form or another. But today, the only thing you can use that Nano for are things that involve static trees. So as I said, ray tracing is sort of the prime example, but actually the way that this is used in Houdini today is for collision detection. So imagine that you have a class simulation or some character simulation, and you're actually representing the collision geometry as an implicit signed distance field. And that's a brilliant use case for NanoVDB, right? Because all you have to do is you do very fast queries into the volume data structure to compute inside, outside, and closest point transform. Oh, sorry, go ahead.
That's right. I was going to address another question if you were going to carry on.
Oh, yeah, please do.
Yeah, so one, is there any example, is there any example of usage of OpenVDB on HPC cluster using distributed memory parallelization or hybrid open MPI/TBB? I don't think there's an example that I can point to, but it's something that we're very interested in pursuing. I think it appears in the roadmap. It's been brought up before. Using OpenMPI specifically for distributed VDB tasks would be very interesting to pursue. It would still obviously be parallel under the hood. Each individual cluster would have would be able to leverage the OpenVDB's multi-threaded tools, but we'd look to distribute the work with some kind of halo communication. Jeff, is you going to chime in? Yeah.
Yeah, because here's the example Dan had at SIGGRAPH a few years back of the distributed fluid solver based on VDB. Yeah. And likewise, there's a toolkit example in Houdini now of doing slice distribution of VDBs. So those are two examples of people trying to do distribution through.
Yeah, so the short story is that there are several examples of people that have done it and are doing it. But it's not part of the distribution yet, and that's actually what's listed under the major proposals on the roadmap. I think Nick is trying to see if he can possibly share some of the code that you guys are using at DNEC that uses MPI.
Yeah, so my experience with this is specifically of OpenMPI, and it is completely possible. It's a huge task. So, and it would be to design a kind of a generic framework to work with OpenVDB and all of its tools as well. So, but if it's good to know that other people are also interested in this.
Right.
Ken, is there any other?
Yeah, there's a question about what version of GSLL does NanoVDB require. Actually, I don't know. I can definitely find out, but I don't know. So I encourage whoever submitted that to maybe shoot me an email directly, and I promise to find out for you. Will Bright for you will know.
There's one. Is there any example how to extract sharp features when doing mesh to volume back to volume to mesh?
Oh.
Is this part of the Houdini toolkit? Is this what we brought up before? Yeah.
Yeah, I think it is.
The best example we have is the Houdini OpenVDB Houdini VDB 2 polygons node, which I think has all the code in like open source there for how you have to do it. It calls into Houdini functions all the time, so you'd have to figure out the equivalent for polygons are, but you'd have to do that anyways for whatever your local polygon library is. But we did recognize this is something missing from the default toolkit. Ideally, there would be something that does it entirely in VDB land. If you make something like that, please contribute it to the project.
I think the main problem is that the OpenVDB library doesn't really have a very sophisticated mesh data structure. So it's not easy for us to provide an example outside of a DCC that has its own mesh data structure like Houdini. But the idea itself is actually quite straightforward. The idea is that you use the original mesh to sort of project the sharp features of the new mesh onto, and that's what allows you to preserve these very sharp corners when you're doing, let's say, for instance, when you're doing CSG operations. Let's say you're breaking up a structure and you want to have a swap frame, so you want to pre-fracture everything, but you want to do it in a way that's sort of seamless, and that's a great application for this. So you do your volumetric CSG. That in itself actually will create creases, but then this mesh extraction tool will allow you to project the new mesh onto the original mesh, such that these creases are completely gone. But we can try and see if we can provide an example in OpenVDB itself. It's just not so straightforward.
And question: any plans to extend NanoVDB to multi-GPU?
Yes, definitely.
Cool. Easy answer.
I think I've mentioned this before, but I'll say it one more time. So what we're releasing today is a beta release, right? It's not a production release. You're absolutely encouraged to pick it up and kick tires and give us feedback. And as I mentioned, Houdini is already going to ship with it, but we will be making changes. We will be making improvements. So yeah, let us know if there are things that are missing that you'd like to see added to it. And then hopefully it will be in a production release before the end of this year. That's at least my goal.
Does NanoVDB currently support isosurface extraction and level set conversion on the GPU?
No, it does not. But again, that is something that we've talked about, something we're looking into. Whether it will be in NanoVDB or some other GPU library, I don't know. But I think it's fair to say it's coming.
And I think you addressed the GLSL question, weren't sure, but next one was, as far as I understand, NanoVDB is focused on ray tracing. Would 3D printing benefit from NanoVDB too?
That's a good question. It depends on what you use it for. Like if you're actually manipulating the volume, changing the tree structure, probably not. If you're obviously if anything that you're using a static sparse volume for would be a great candidate for NanoVDB. But if you're dynamically modifying it, probably not.
I just want to clarify, it's not about ray tracing. That's how it was originally discussed, but it's actually very much just about having a sparse volume on the GPU. And so like everything we used was not ray tracing. And so I could think of a lot of things for 3D printing that would work right off the bat without having to manipulate topology, so it would work with it.
Right. No, that's true. That is true. And in fact, Jeff, you're the first one to sort of break the tradition and use it for something completely different. Your collision detection, right?
Got a good one here. Where's the best forum location? Is it the Google forum group or via the ASWF? That's a great question. We ask ourselves that every week.
I think it's the Google forum.
I think the Google forum we've been looking at as more of an open discussion about high-level discussion about tools and features, whereas again we do use GitHub issues as well for more specific software specific issues with the software. But yeah, I don't think we're currently using the ASWF alias dev alias for too much discussion that doesn't revolve around the TSC meetings. I agree that it would be good to try and consolidate some of these. In major proposals, how does multi-resolution VDB differ from current VDB? I think the main thing here, so there is actually again, Ken, I guess I'll let you talk to this because it was your implementation of the current multi-grid support that exists in VDB.
Right. So there is sort of limited, what I'd call limited support for multi-resolution grids in VDB today through the tool called multi-res grid, and essentially it builds again, it's for static applications, and it builds a level of detail hierarchy of grids with progressively coarser voxel sampling. So imagine that you have a high resolution, let's say you have a high resolution SDF that you want to use for collision detection. You can then build a hierarchy of trees with progressively coarser and coarser resolution that you can probe. But the proposal that's listed in the roadmap is something entirely different. It's actually so we've been in dialogue with the Bifrost team at Autodesk, and they have a very cool multi-resolution volumetric grid that's dynamic. And as far as I understand, they're actually using OpenVDB for I/O. So we've been looking into, unfortunately, it's not moving very fast. I think the ball is in our court, to be honest. But we've been talking with them about adopting essentially their grid structure, and that's an adaptive grid structure. So maybe it's worth pointing out when we say multi-resolution and adaptive, adaptivity can mean many different things. And in this case, what we mean by multi-resolution is the fact that a grid value can be sampled at different resolutions. So a single value may exist at different levels in this tree structure. Whereas currently in VDB, a grid value ijk only exists at a one level. It can either be at a leaf node at the finest resolution, or it can be higher up in the tree at a tile. The fact that VDB has a very, very high fan-out factor. I remember the diagram I showed you with 4 different levels, demonstrating that it's a very shallow tree. The reason it's so shallow is that the fan-out factor is very high. That's great for access, but it's not very good for adaptivity, because the refinement in resolution when you jump from one level to the next is very big. So you can sort of contrast it to an octree, which has ideal refinement because it's 2 in each coordinate direction. So yeah, it's a long way of saying there is some support for multi-resolution today in VDB, but if you're looking for something that's adaptive dynamic, you still have to wait a bit.
Just before we go on to the next question, Jeff makes a good point. We are considering removing the make files from the VDB distribution. If anyone has any thoughts about that or concerns or doesn't want us to do that, just let us know soon or now. Yeah, just wanted to mention that before we go on to the next question. Ken, one for you. Can NanoVDB use paging or similar methods on the GPU to read large volumes, e.g. production caches, onto the GPU while staying within GPU memory limits? I assume we're talking about streaming to some extent here.
Not today, but there is another team at NVIDIA that's working on this. So NVIDIA has a commercial product called Index. It's a scientific visualization tool that allows you to visualize very, very large scientific data sets, like typically stuff that comes out of HPC. And it actually uses, obviously, multiple GPUs. It actually uses API, and they're working on on adding out-of-core support to NanoVDB. I'm hoping, I don't know for sure, but I'm hoping that we can share that back. But the idea of using memory pools is a great idea, and obviously this is what you need to have a dynamic data structure on the GPU. And because NanoVDB doesn't have this pool, that's also why it's limited. It's not able to modify the tree yet.
last one again from was about communication. How about a Slack or Discord group? I don't think we're opposed to any forum type for discussion. It's perhaps something we should bring up in one of our steering committees following.
I would love Slack. I have great experience with it. I can't remember, does ASWF have a Slack channel or a Slack account?
Yeah, we do have a Slack group.
Yes, we do. So go slack.aswf.io, and there's an OpenVDB channel on there.
Oh, there it is. Wow. Okay. There you go. Maybe we should start using it. Cool.
Cool.
Yeah, looks like we've exhausted all the questions. Is there anything more you want to say about the roadmap, Nick?
I don't.
Is there anything you could say about, like, when do you think AX will be available? You think, later this year, or
I mean,
or you don't know?
AX is ready to go, I think.
Okay.
It still needs to be vetted thoroughly by the TSC. We've had a good round on the front end language, on the actual language specifically, so I think that's in pretty solid state. So we would like to see it, I think, in a 7.2 or 8 release, basically the next release of VDB.
Cool.
I don't know if anyone else has any comments on the roadmap.
Yeah, I can make a few quick comments. But just going to quickly mention that, like, some of our focus over the last year or so, and I imagine going forward will be the case as well, is trying to kind of streamline the library and the tree hierarchy a little bit. Over the years, it's kind of grown in size, and there's more and more tools that are in the tree hierarchy, and especially with examples like NanoVDB, where a very lightweight hierarchy has a lot of benefits. We're trying to sort of pull some of those tools out. And we've also found some performance improvements through some of those tools being separate, so that we can use different kind of techniques for parallelizing that makes them a bit faster. And so, yeah, so there's some of the work that's happening with that. And then obviously framework, building stuff, improving the CMake. We've done a huge amount of work on the CMake over the last year or so, and there's a lot more to do with that, I think, but it's getting to a stage where it's becoming a lot more mature. So definitely we're trying to formalize that, and that's giving us opportunities to try and reorganize the code base a little bit, move things around a bit, and just kind of tidy it up and modernize it in a few places where it needs to be. Yeah, I haven't got any more comments in terms of the different features that are there. We need to kind of discuss some of the roadmap items and figure out which are the big kind of priorities. But yeah, for the time being, AX and NanoVDB remain the two sort of focus points at the moment.
One last question, Ken. How does NanoVDB compare against GVDB?
Oh, I honestly don't know. So I think GVDB. So actually, the Rama, the core architect of GVDB, has left NVIDIA, and I believe the project is not being developed more. So NVIDIA itself is actually is moving on to another project that unfortunately I can't talk about. But in terms of comparison between GVDB and NanoVDB, it's a little bit apples and bananas, because GVDB allows you to do simulation. NanoVDB does not. NanoVDB is focusing on rendering. I'm pretty sure GVDB can also do ray tracing. I have not compared the two. I would be surprised if there's a big performance difference. There really shouldn't be, because underneath, I think GVDB is using a data structure that's fairly similar to the VDB data structure. So yeah, that's actually a good question. I should check that out.
I see a comment came in that apparently GVDB will be out of support for NanoVDB in a few days.
Oh, sorry, GVDB will be out of support in a few days?
No, add-in support for NanoVDB in a few days. It's in the chat.
Oh, cool. Okay, sounds like someone is still working on it. That is cool. Okay, I take back what I said then.
There was another question I accidentally dismissed. That was, oh, is it over?
No, I just ended the screen share.
What was the license for this and can be used for commercial development? I hope it can be used for commercial development because Houdini is using it for commercial development. It's
oh, I forgot to mention that. There's a paying license. No, it's the exact same license as OpenVDB, right? So the same restrictions or lack of as OpenVDB. So yes, you can definitely use it for commercial software.
If we have time, super quickly, one last one. Are there any examples of how to load triangle meshes to NanoVDB? I guess you could go through OpenVDB to a NanoVDB.
Yes, that would be the workflow today. So think of NanoVDB as a bridge to the GPU, where you can do anything on the GPU that involves a static tree. And as I mentioned many times before, rendering is one example, collision detection is another one. I'm sure there's a bunch of other examples that we haven't even thought of yet. But in terms of authoring VDBs from a mesh, you currently have to go through OpenVDB. But that may change. So cool. I think we're spot on.
Yep.
Yeah. So thanks everyone for dialing in and for listening to this presentation. If you have more questions, by all means, please reach out. You can use email. You can use the two forums that we talked about, and we'll try and keep you up to date. Cheers.
Thank you, everyone. Cheers.